So today we're going to start the unit on types of chemical reactions and solution stoichiometry. So for today we're going to discuss aqueous solutions. So do an introduction and also talk about the stoichiometry involved with aqueous solutions. So first of all, what is an aqueous solution? It's basically a solution where water is the dissolving medium, or what's called the solvent. And we'll talk about solvent in a second. Aqueous solutions have many uses, and there are lots of aqueous solutions out there. In fact, you probably consume them all the time. Kool-Aid, iced tea, all of that stuff is basically an aqueous solution. Okay, so since it contains water, let's talk a little bit about water. Water is really important because it's capable of dissolving lots of different types of substances, and the reason for that is based on its chemical structure. Water has a bent shape, so you've got your oxygen and then your two hydrogens, okay, and so it gives it that bent shape because we know we have our two lone pairs up here pushing the hydrogens down. The O to H bonds are polar covalent, which means, if you remember from CP chemistry, that the electrons are shared but not equally. Oxygen is more electronegative, so it has the partial negative. Each hydrogen is partially positive, which means the dipole is going to go toward the oxygen. So each of those bonds electrons are not shared equally. Because of its bent shape and this polar covalent bond, it gives the molecule an overall dipole. Towards the oxygen, or in that general direction. So this makes water a polar molecule. Okay, so according to like dissolves like, it will react with other polar things. Okay, so hydration is the interaction between solute particles and water. So it's basically dissolving. So the hydration of salt causes the ion to fall apart or to dissolve. Remember, salt is NaCl, or sodium chloride. So the negative chlorine attracts to the positive hydrogen. Remember, we said that the hydrogen had a partial positive charge, and the positive sodium attracts to the partially negative oxygen, and so it pulls that ion apart because the chlorine and the sodium are attracted to different charges. When ionic compounds dissolve in water, they break up into individual cations and anions. So saying that something dissolves isn't always the most correct term. In this case, we would say it dissociates because it's breaking apart into its ions. Other things can dissolve and not dissociate. Okay, so speaking of that, let's talk about solubility. So the solubility of an ionic compound depends on the difference between the attraction of the ion for each other and the attraction of the ions for water. If the attraction of the ions for water is greater, it's going to dissociate. Non-ionic substances can also be soluble in water, but they have to contain similar properties to water. So when we talk about like dissolves like, if something is polar, water is polar, they'll dissolve in each other. Non-polar substances, so mainly fats, any type of fat, are not soluble in water because they're non-polar. Water is polar, that they don't mix. Okay, and remember, soluble means it's going to dissolve, not necessarily dissociate. Okay, so we've talked about solute, solvent, so let's define those. The solute is the substance that gets dissolved. So in the in the salt water example, salt was the solute. A solvent is the substance that does the dissolving. Now for aqueous solutions, that's going to be water. It doesn't always have to be water. Other things can be solvents also. So these terms are really similar, and it's easy to get them mixed up. So here's the way I remember it. If you look at the alphabet, A, B, C, and then you get to T, U, V, W. Well, U, to me, represents solute, because it has a U in it. The V represents solvent, and the W represents water. And since water is closer to the V than it is to the U, that tells me that water must be the solvent. Well, I know that water dissolves things. So that's the purpose of the solvent. It does the dissolving. Well, if the solvent does the dissolving, that must mean that the solute is the one that gets dissolved. Okay, so that's how I remember it. However you need to come up with to remember it is up to you. But the terms are so similar, it's easy to get them confused. Okay, so we can also, besides using solubility to characterize solutions, we can also use what's called electrical conductivity. And this is how well a solution will conduct electricity. Strong electrolytes are contained in a solution that is good at conducting electricity. Weak electrolytes will still conduct electricity, but your light bulb's not going to be as bright as if it was with a strong electrolyte. And non-electrolytes will not conduct electricity at all. And so we can use solubility to describe solutions. We can also use this electrical conductivity. So let's talk about strong electrolytes. In order to be a strong electrolyte and conduct electricity really well, the substances have to completely ionize or dissociate or break apart into the ions. So salt, NaCl, is a strong electrolyte because it completely breaks apart into its ions. This allows the electrons to move freely, which is what conducts electricity. So we can break strong electrolytes up into three classes. Soluble salts, NaCl will be one of those, strong acids, or strong bases. So let's look at soluble salts. Soluble salts completely break apart into their ions because we know that has to happen in order to be really good at conducting electricity. So salt is an example of this. So if we look at the reaction, we've got our solid salt. We're going to put it in some water, so we write water over the arrow, and then we're breaking it up into our sodium ions and our chlorine ions. Okay, take a look at the picture. See how the oxygen is surrounding the sodium ion, and then the hydrogens from the water are surrounding the chlorine ion. So it's pulling apart that sodium and chlorine based on its attraction to either oxygen or hydrogen. Okay, let's look at strong acids. Strong acids break up into the H+ ion and then the anion, which remember is the negative part, when dissolved in water. So H2SO4, HNO3, and HCl are aqueous solutions and should always be written with an AQ. Okay, so because these are being mixed with water, we're writing them as AQ. Okay, a strong acid completely dissociates into ions, just like the soluble salt. So if we have 100 molecules of hydrochloric acid and we put it in water, because it's going to completely dissociate, that's going to give us 100 H+ ions and 100 Cl- ions, or our anion. Okay, so if we have 100 of the compound, we have 100 of each of the ions. Okay, if we look at sulfuric acid has two hydrogens. Well, they're going to come off one at a time. So initially, sulfuric acid is going to yield H+ and HSO4-. And we'll talk a lot more about this. We have a whole chapter on acids and bases. Okay, so if we look at the equation for sulfuric acid in water is going to yield H+, AQ, plus HSO4-. Okay, let's look at strong bases. Well, bases usually contain a hydroxide ion. So a strong base is going to dissolve to produce the cation, which is the positive part, and the hydroxide ion. Basic solutions will usually be water and either sodium hydroxide or potassium hydroxide. So if we look at the reaction for potassium hydroxide, we're going to react it in water and break it up into its ions. Here's our cation, and here's our hydroxide ion. Okay, weak electrolytes. Remember we said that those kind of conducted electricity. So what this means is that not all of their ions are going to dissociate, just a few. And so the most common form of a weak electrolyte is either a weak acid or a weak base. And so, for example, acetic acid is HC2H3O2. Now you'll notice there's more than one hydrogen. We've got one in the front and then three here. It's written that way specifically because we put the acidic hydrogens first, and then the non-acidic hydrogens are written later. So this gives some information about how the compound is bonded. What that means is that this is your acidic hydrogen. This could potentially come off to produce that H+ ion and then the C2H3O2 ion. So if we look at a reaction, we've got HC2H3O2, AQ. Notice this arrow is going both directions. Because it's not going to completely dissociate, it can go both ways. And here we have it breaking up into its ions. Okay, so ammonia is a weak base. Okay, and so here we've got it reacting with water, and it's producing the ammonium ion and then the hydroxide ion. Okay, the third part we talked about were non-electrolytes, which don't conduct electricity in water at all, but they can dissolve but they're not going to produce any ions, or they're not going to dissociate. Okay, so ethanol is an example, and sugar is also an example. So here we've got a big sugar crystal. Okay, you can see it's not breaking apart. It's still the sugar molecule. Okay, and so each of these represents a sugar molecule, but it's still being surrounded by water and broken apart. So if you dissolve sugar in water, it's going to become one liquid solution, but it doesn't mean that it's dissociating into its ions. Okay, they dissolve, but their molecules do not break apart.